All right, we just talked about enthalpy and free energy, mostly enthalpy, and now let's go through a calculation in this module. So here's the problem statement, the problem I want you to address. What I want you to do is calculate enthalpy content, like we talked about in the previous module for aluminum, Al, and its oxide, Al2O3, at two different temperatures, 298K and also 900K. And I give you the following data, heat capacity and otherwise, to be able to solve this. So take a look at this, see if you can answer this in the quiz, and then come back and we'll work it together. All right, so now let's go over the enthalpy calculation that you saw in the previous slide. So we're trying to get the enthalpy content of both aluminum and aluminum oxide at both temperatures of 298 and 900 K. So let's start with aluminum. And so the previous equation that we saw for enthalpy content, and enthalpy, was enthalpy of the material at a given temperature, and we'll define this as 900, minus the enthalpy content of the same substance at the reference, which was 298, was equal to the integral between those temperatures of the heat capacity. So we can go ahead and swap in this, which is the heat capacity, and you can see that heat capacity is a function of temperature. So we're given it as a function of temperature within a given temperature range. And if you're kind of looking at the ranges, so typically it'll be the standard state of 298, and then this will most likely be some type of phase transformation, like aluminum going to liquid aluminum. So in this case, we're given that, and so we can go ahead and sub in the heat capacity. And this is the integral with respect to temperature. So basically what we need to do to solve for this is to integrate this expression with respect to temperature. But the first thing that I want to draw your attention to is over here, right? So we want both of these, but we already know that the enthalpy of a material at standard temperature, so the enthalpy formation at that temperature for an element is 0, right? So aluminum is an element, and so this goes to 0. So we already know, sorry about that, aluminum 298 is equal to 0. So really, this whole expression is what the enthalpy content of aluminum at 900 is, right? So that's what we're solving for. So if we solve for that, we have two terms, right, when we're taking the integral. So we've got the constant 20.7, and then we've got this term in terms of t. So when you're dealing with a constant, it's going to be 20.7 times t at both those temperatures, so it ends up being T2 minus T1. Then when we're dealing with t to the 1 power, it's going to end up being this term divided by the new exponent, which is going to be t squared. So we have T2 squared minus T1 squared. So I'm going ahead and evaluating them at the two temperatures. All right, so T2 is 900, T1 is 298, and so when I put all of this in, I get 16,932, and from the expression here, all of these heat capacities are in terms of joules per mole. So this is joules per mole. And so we can also say, since this is such a large number, we can just say this is 16.9 kilojoules per mole for the enthalpy content of aluminum at 900. So that's the first part that it's asking us about. So next, we'll go and look at the enthalpy content of Al2O3. All right, so now let's look at the enthalpy content of the ceramic Al2O3. And so I've left heat capacity information so you can see it up here. And let's go ahead and rewrite that formula that we had before, just swapping in Al2O3. So the enthalpy content at 900 minus the enthalpy content at 298 is equal to the integral that we have. And so that's, again, I can sub in the version up here. And in this one, we see that we have an additional term of t of minus 2. And this is respect to temperature. Okay, so to solve for this now, we are going to solve the integral first. So just like we did before, we take the integral and I'll go ahead and evaluate each term. So this was the constant. So same thing, it's going to be 106.6 multiplied by t evaluated each term. So t2 minus t1 plus we had a t term. Messed that up. It should be a t here. So this is the constant divided by 2, and then t2 squared minus t1 squared, just like we had before. And then here we have a negative, so it's the same rule, the plus 1 rule, and so we add 1, so this should be t to the minus 1. So we're going to take the constant divided by minus 1, and then we have t2 to the minus 1 minus t1 to the minus 1, right? So it's the same rule for all of these powers. And so again, we have 900 and 298. And so with this, if we just plug in all those temperatures into this expression, we get 64,194.8, and that's in joules per mole because of the units of heat capacity here. All right, so here at this point, we have the difference between the two. However, in this case, we can't make the assumption that we did before because this isn't an element, right? So this doesn't cancel out to 0. So we actually need to know the value of this. And I forgot this, so I will put it in the slide, in the previous slide, so you see that. But this value, the enthalpy of formation for Al2O3 at 298 is given to us. So I apologize for that. I'll fix it in the slide. And that's kilojoules per mole. So we can use that, but we have to have that value or be able to look it up to be able to solve for the value here at 298. So putting that into this expression that we have for the difference, we can get that the enthalpy of Al2O3 at 900 is going to be that value plus the integral that we just had, which is 64.2 if we use kilojoules per mole. And that gives us a value of, for 900, gives us a value of minus 1,611.5 kilojoules per mole. So there's not too much to this other than we need to know the heat capacities, take the integrals, and then we are able to find the enthalpy contents at whatever temperature as long as it's in these temperature ranges.